Today, we're digging into software engineering. And we're not just talking about tapping out lines of code. We're going to explore how teams of actual people manage to build the gigantic, complex digital worlds we all live in. Systems so intricate they seem almost impossible to create.
But to really get how we build the impossible, we have to start with a more basic question. We've all been there, right? Buggy software, apps that are delayed forever, or projects that just disappear. Why is this so common? Why is building software so incredibly hard?
Well, it's not just a feeling you have. The data shows this is a huge, long-standing problem that people in the field actually call the software crisis. Just look at this report from the Standish Group. It's kind of sobering. Nearly half of all projects are late or over budget. Almost a quarter of them just get canceled completely. Only about 28%, a little more than 1 in 4, are actually considered a success. And this isn't a new thing. It's a battle the industry's been fighting for decades. So what's the deal? What's the root cause of this crisis? It's not lazy programmers or bad managers. Not really. The real issue is much, much more fundamental. It's a head-on collision between the sheer complexity of software and the built-in, hardwired limits of our own brains. Okay, to really get this, we gotta take a quick look at how our brains work. Cognitive science talks about something called short-term memory. The easiest way to think about it is like your brain's RAM. It's the mental desktop you use to actively juggle ideas and process information. But, and this is the absolute key, it is tiny. Just how tiny are we talking? Well, a lot of research points to what's famously called the magical number 7, give or take 2. And that's it. On average, you, me, all of us, can only hold about 7 distinct ideas or items in our active memory at any given time. It's a real biological bottleneck. And this is where it all falls apart. A really simple program might have, a few variables you need to track. Easy enough to keep in your head. But a modern app, it has thousands, maybe millions. The number of ways they can all interact with each other doesn't just grow. It grows exponentially. It blows right past that magical number 7 almost instantly, making it physically impossible for any single person to understand the whole system at once. So, if our brains are basically set up to fail at this, how on earth do we build anything complex at all? Well, this is where the engineering part of software engineering saves the day. It gives us 2 incredibly powerful core principles for taming that insane complexity. And these 2 secret weapons are abstraction and decomposition. Honestly, they're the main tools we have to manage the chaos of a big software project. Abstraction is all about simplifying, and decomposition is all about dividing. Let's take a quick look at both. First up, abstraction. This is the art of creating a simplified model of something. You basically, on purpose, ignore all the messy, complicated details so you can focus only on the part of the problem that matters to you right now. A perfect real-world example is just a regular map. A roadmap is an abstraction, right? It shows you roads and cities, but it hides every single house and tree, because you don't need that to get from point A to point B. It's a simplified model for a specific purpose. We do this all the time to make sense of our crazy world. Okay, our second weapon is decomposition. It's pretty simple. If a problem is too big and scary to fit in your head, you just break it down. You divide and conquer. The whole goal is to chop a massive, overwhelming challenge into a bunch of small, manageable pieces that are as independent as possible, so you can solve them one at a time. The classic analogy here is the bundle of sticks. If you try to snap a whole thick bundle all at once, it's basically impossible. Your hands just can't do it. But if you pull out one stick at a time, breaking each one is super easy. Decomposition is just the art of unbundling those sticks, so you can focus on one at a time. So how do these big ideas, abstraction and decomposition, actually show up when people are building software? Well, they're the foundation for 2 major and pretty different ways of getting things done. So first, you have the traditional way, called the waterfall model. You can think of this like building from a very detailed, rigid blueprint. It's a straight line, a linear process where you have to completely finish one step before you're even allowed to start the next. You do all the analysis, then you do all the design, then you do all the coding. There's almost no room to go back and make changes. And on the other end of the spectrum, you have the more modern approach, agile development. Instead of one giant blueprint, agile is more like building with Legos, smaller, more flexible blocks. It breaks the whole project down into these small, iterative cycles. And at the end of every little cycle, you have a tiny working piece of the software.
This lets the team constantly learn and adapt as they go because, let's face it, with really complex stuff, you can never know everything at the start. This quote is one of the core values from the Agile Manifesto, and it just perfectly sums up the difference. Waterfall is all about following a pre-made plan perfectly. Agile assumes that plan is probably wrong, and it's built to embrace change and uncertainty. Now, no matter what method you use, waterfall, agile, anything in between, there's one economic reality that rules everything in software, and it's all about mistakes, or bugs, and specifically when you find them.
So let me ask you a question. If a developer makes a mistake, when do you think it's most expensive to fix? Is it during the early planning stages, in the middle of coding, or way at the end, after the product has already been shipped to customers?
The answer is not even close. The cost to fix a bug isn't a straight line, it's exponential. A misunderstanding in the initial requirements that doesn't get caught until the software is out in the world, that can cost hundreds, sometimes thousands of times more to fix than if it had just been caught on day one.
And this exponential cost is exactly why so much time and money gets poured into testing. For a typical software project, testing eats up a shocking 40 to 50% of the entire development cost. I mean, think about that. That's almost half the budget. It seems like a lot, but it's an absolute bargain compared to the cost of fixing those same mistakes after the fact. This one economic truth drives almost everything in modern software engineering. The whole game is to find and fix problems as early as humanly possible, when they're still cheap and easy to deal with.
Which really brings us to the big takeaway here. Software engineering isn't just about being a genius coder. It's a structured discipline. It's full of principles and processes and tools that were all designed for one single purpose: to let teams of normal people work together to solve problems that are way too complex for any one brain to handle alone. These are really powerful tools for taming complexity. And it kind of leaves us with one last question to chew on. As software keeps building more and more of our world, how can we take these same principles, abstraction and decomposition, and use them to manage the overwhelming complexity in other parts of our own lives?